did some synthetic things that a sophomore organic chemist would not have done. But I guess I was just passing it on because she asked me.
My question is more like when you're talking with him, you probably can recognize how much he's complete, like because if he's just knowing organic chemistry, which we not so much interested in.
Yes.
Maybe you need to learn everything from scratch and some. He's a second year user, so it means he was. Do you know was he taking this courses? Was he done with all this?
I don't know. I don't really talk to him much because I think there's a reason why he wants to leave Simu. Which yeah. So I passed it on because Jasmine, Dr. Yang's student, asked me if either of you would want him as a graduate student.
We need to discuss this. So first of all, we need to see his reach.
Yes. So
he needs to not contact you, but contact us.
Oh no, he contacted Dr. Yang. Yang talked to his student.
No, I understand. He's just asking some kind of opinion or whatever. But this is not enough. We need to see some motivation and really reach.
Yes.
Because about this step. So he needs to send email to us explaining his situation, giving as much details as he can for convincing us that it's not because he was taken out from everywhere, but because he really wants to try computational chemistry. Although we know the truth.
Yeah. Okay, I'll tell Jasmine that you would have to be convinced. Okay.
And his classes, if he can give this information to us in his email about his progress in required courses, 700, like there are 4 core 700 courses, including physical chemistry. How's it called? So survey and physical chemistry, survey on organic chemistry, survey. Well, yeah. So he is supposed to be, if he is a good, strong student, by second year he's actually all these 4 courses are expected to be taken just in the first year. Usually it's not the case, but at least we need to know how successful he is with courses.
And he's also supposed to have his maxes done. Or his maxes done.
You said it's third year or second year?
Second.
Then maxi is not done.
No, it's supposed to be done now. Because your second year seminar can be related to your research, your minis can be related to your research, and I believe how they have it organized, which I could be wrong because I haven't looked at it. You do your second year seminar.
This is on the paper. No one was able to do that in the second year. I didn't hear any case so far. When it was discussed when we changed this program, this was kind of a goal. The problem is you cannot have a second year the seminar you have in the fall, right? So which means you probably will have your mini in spring second year, and then it's either summer, which usually people don't do in summer, but fall, the beginning of the third year, this is when usually people have their maxi. If done with courses, because if they don't done with it, it's a final exam, not final. It's kind of connected to
I need to leave. To disconnect.
Okay. Okay, but I think we kind of answered the question.
Okay. And the student in Dr. Sibi group, that
Hi Aaron. Hi Ewan. Hi Fatima. Many thanks for connecting, and I believe it is good chance to let Aaron to practice his preparation to this step towards degree. So, Aaron, I saw you were testing the connection of sharing screen. Did it work, or would you prefer me to show your slides?
I was just testing it now. Is my audio delayed?
Right now we hear you. We can hear you.
So I guess we could just try it like this and see if it works, and if it doesn't, we can transition.
Okay, yeah, I will be a backup.
Okay, so I guess the goal of this presentation is a comprehensive exam. So it's similar to like a second year seminar, or not seminar, but kind of like a comprehensive exam that they do for second year students in chemistry. And I guess it's mostly just like a hard background information that present, and then the main part is at the end. There's a research proposal. So we have to present to my committee. So the structure of the talk is just the first 10 minutes of just kind of background, getting by carving out my area in my research field. Then 10 minutes on research methods that we use in our group in comparison to competitors. And then after that, about 10, 15 minutes on work that's already been published, showing application of our method. And then like the last 10, 15 minutes on the research proposal. So that's kind of what I'm aiming for this presentation. So the first thing I would present is just a brief background resume of where I'm at for my PhD studies. So right now I'm a fourth year student in the interdisciplinary materials and nanotech PhD program.
Does everyone does anyone see? Just a second. Does anyone see Aaron's slides? They were in and now they're out. Okay.
Did they disappear again?
It disappears again. Now it appears. It stays.
And when I go into the present, it disappears.
Yeah, when you click present slides, it disappears, right?
I guess.
If you do not have movies, then I think PDF that I can show you your work fine.
I do have a couple of movies, but they're not like, they can be left out.
Okay. Oh, we can switch back to your screen when there will be critical important movies.
Okay. Everyone see it? Everyone see? Can people hear me?
Yes, I can.
So this is what I was talking about for my brief resume. So I guess I've lived two separate lives, or two different lives during my graduate career. So a lot of my time I spent working with Dimitri, doing computational modeling of materials, but also as a side kind of a project I worked with Eric Hobby, the co-advisor, by synthesizing and using competitive separation techniques to characterize nanomaterials. And so those are, I guess, the two research areas that I've spent most of my graduate career researching so far. And it doesn't seem like it would be synergistic, but having to deal with the physical samples themselves, I've had to learn a lot about the chemistry of these materials. So it's kind of helped reinforce different aspects behind nanomaterials. So that's a lot of the work that I've done. And then on the right is just an overview of peer-reviewed papers that have been published so far. So to count, there have been 7 journals, and then we have a couple in progress between me and Dimitri, and then me and Eric as well. That will be coming up hopefully sometime this summer. And then won a couple of graduate student awards as well. So 2 years ago, I got a best poster presentation. And then this year, at the same conference, I got a travel award, and then I won an on-campus student research award presentation as well. And then I've also had various poster and oral presentations at conferences too. So during my 4 years, I've gotten, I filled in my resume quite a bit. And so as a student in materials and nanotechnology, whenever I go home to family and try to describe what is it exactly I research, it's not intuitive to describe material science, because on one hand, you could say it's like a technical description would be it's an interdisciplinary field between physicists, chemists, biochemists to work on cutting edge problems of the day. And that usually leaves at least my relatives more confused. So I usually try to give them some perspective of material science just through like a short little history. So that's kind of how I'll demonstrate my research in the field, or my place within the research field. And so if I said I was a material scientist like 2,000 years ago in antiquity, I would have been, I can remember the phrase that. So I guess 2,000 years ago, when people were trying to build society, they looked around and said, well, what do we have to deal with? Usually we have the 4 elements: water, wind, fire, and earth. And then they use those resources to make different sorts of materials. So you can use natural products from places such as sheep to make cloth, or in today's terms, we would call those like natural polymers, that people had to learn how to process and then work into clothing and fabrics and blankets. But then they also had to be very crafty in how to develop, or to make furnaces hot enough to be able to work ceramics and metals to work in the tools. And they also had to be crafty in how to build complicated aqueducts to supply water into town. And so if I said I was a material scientist during the Antiquity, these are the types of problems I would have been working on. That kind of interface between everyday life and then like the technical problems of how to solve them. And then that's what material scientists would have been for most of history. Then up to about 200, 150 years ago, people have discovered that the materials they've been working with, they have a finer structure to them. So if you go look deep enough down, you find that all the materials are made up of atoms, which are listed out or have been characterized on periodic tables. And then through different combinations of these atoms, you can make like periodic solids, like ceramics or metal that are infinitely big, or you can make organic molecules, which is kind of the realm of where chemistry is. And then there was mostly physicists that would deal with solids. So you have these two separate fields that kind of had their own tools on how to characterize these materials. But within the last, 50 years or so, people have been trying to get crafty and think, how could we make these inorganic solids into the size of molecules? And then that's where nanomaterials come in for material science. So you can say, what if we took like graphite, which is just a chunk of rock, which is basically carbon, planar carbon, which are just laid on top of each other. But it's possible to just take like a flake, like a one atom thick flake of that graphite to make graphene, a two-dimensional material. And that gives unique properties because along, say, the Z direction, there's the charges are heavily confined, whereas in X and Y, they can move out the entire plane. So those give rise to peculiar two-dimensional properties of graphene. But then you can also imagine what if you took that flake of graphene, you could roll it into a tube to make a one-dimensional material, like a carbon nanotube, or you could try to roll it into a ball, make these carbon buckyballs. And so, with each type of dimensionality, you can tune these materials, which I'll talk about further. And I'll just mention that I focused on these carbon compounds because they're simpler to talk about, but there's no, in principle, there's no limitation. But if you're a crafty enough chemist, you can make these nanomaterials out of pretty much any chemical composition. So there's a lot of fine tuning you can do to these materials. And so that's kind of the background of how we've gotten to the point of wanting to research nanomaterials. But like, what's the big deal behind them, or kind of what's the promise that they give? And so, for me personally, I focus on electronic processes in nanomaterials. And so, in that context, compared the promise of nanomaterials is that you can kind of engineer the rates of excited-state processes in these materials. And so, or like a general way to describe rates of rates of processes, so this K, they're usually described by this V interaction, which describes like how strongly two like charges interact with each other or with the lattice. And then it also depends on like the density of electronic states. And so in this figure below, just from changing the dimensionality of the material, you can drastically change their electronic density of states. What you can see with the bulk is essentially like a continuous distribution of electronic states. If you put it into, say, a quantum dot, you get very narrow lines. So you can try to use quantum dots for like little sensors So you can kind of fine-tune energy differences between transitions. So you can change electronic states, but you can also try to engineer the rates by changing the strength of the interaction in these materials. And so for, I guess a simple example of this is if you want to make material emit light, you have to create what's called an electron hole pair. And essentially for them to emit light, you have to have the electron hole in a crude sense collide into each other. That's not technically exactly how it happens, but just for this example, you can kind of imagine for to emit light, they have to collide. And so to show why both materials are generally not very emissive, if you take these electron holes and put them into a large continuous solid, if you think of them as point particles, like they have to, or they have a very low probability of running into each other, just because they exist in such a large space. If you take that same material and turn it into like a quantum dot, the probability that they ram into each other increases very much.
Good question. So here you talk about rates of the excited state process can be specific. So what kind of excited state process will you describe, like some bond breaking or bond forming process as well?
So I guess excited states of charge carriers.
Okay.
I guess, yeah, it could be bond breaking too for like catalysts, but I guess my main focus is just charge carriers. And so in nanomaterials, you have a lot faster radiative rates, so they're much brighter. And then coupled with the fact that you can finely tune their transition energies, you can try to make these things emit anywhere from the blue to the red region, which is convenient because that's what a lot of our lighting technology is based off of. And so then the end goal of having all this knowledge is to take these nanomaterials, generate charges in them, and then put them into circuits. So whether you try to extract charges from them to create power like a solar cell, or you hook them up to battery sources and try to drive charges into them to emit light. So that's kind of the end goal for studying all these nanomaterials, is to create useful technologies out of them. And to do that, you have to be able to finally tune and understand these processes of charge carriers. And so they show a lot of promise, but I guess I wouldn't be a researcher looking at these problems if there weren't a lot of problems to overcome. And so just to illustrate this, I've created just a little Venn diagram kind of illustrating or just mentioning the different problems that have to be overcome. And so I should probably put a picture in here, but the biggest thing is the surface chemistry and the surface interactions of nanomaterials, because just, I guess in general, surfaces are much higher in energy than the bulk. So if you have a nanomaterial, they're basically all surface. So in some sense, they would rather form together into a bulk than stay as a nanomaterial. And to do that, you have to use crappy surface chemistry where you can attach molecules to the surface of the nanomaterials to try to keep them separated. So that's kind of the main practical problem. And then in terms of the physics, it's just trying to use our already established theories and then applying them to these materials. And then I guess where I live is in this intersection of these Venn diagrams. There's like the impact of surface chemistry and potential defects and impurities on the excited-state dynamics. So that's the general overview of the field that I live in. And there are various approaches to try to characterize these materials. So the most obvious thing that might come to mind for people is using experiments with lasers to track these excited-state dynamics, but with the increased computational power that we've developed over the last couple of decades. Now, you can actually run computer simulations on these nanomaterials and try to describe these excited-state processes. And so that's what these next couple of slides will be. So I'll describe the general processes that we look at and then provide an overview of the methods that we use to describe them. Which slide do you all see right now?
17.
Does it say electronic structure?
It tells modern excited-state dynamics. Electronic structure, DFT.
I guess it skipped a slide, but I guess I'll start here. So essentially, to do our atomistic modeling, we need to be able to compute three things. So we need to compute a reliable ground state electronic structure. We have to be able to compute electron-phonon interactions and then white matter interactions. And so for doing electronic structure calculations, there have been a lot of theory has been developed over the last 50 years. So one of the first ones was Hartree-Fock, which is listed under sorry, I just get caught up. I think the slide that's shown to the group is a little slower than what's presenting.
Okay. Aaron, please.
Okay, it's on the right slide.
Okay, give signal. Just tell next slide or whatever if you feel it is asynchronous.
Okay. popular so-called wave function methods, which as they sound, they use like wave function methods like Schrodinger's equation to solve electronic structure problems. And there's the lowest like complexity one is the Hartree-Fock, which, like I said, is in one sense the simplest because it neglects correlations. But to include better account for correlations, you have to use these higher order methods, like configuration, interaction, tuple cluster, or perturbation theory. But those are generally too expensive for the systems we look at. So for most of the research that we do, we use this so-called density functional theory, which instead of using the wave function as the basis for its theory, more focuses on the density, which is this third equation from the bottom. So from the electronic density, which is, they use it to characterize the entire electronic structure. So it uses this first equation, which is an analog of a Schrodinger equation, with a kinetic energy and potential energy term, to create orbitals. But once it creates the orbitals, you compute a density, and essentially try to solve these equations in a self-consistent manner. And the benefits of this is that the scaling, or the computational scaling is, n, I don't have it on here, but it's n to the third, where n is the number of electrons. So you have, so with today's computing power, that's a feasible like scaling for the model that we try to look at to solve electronic structure problems. But the cons is, or I guess or some people might criticize, is that there are a lot of approximations. If you're trying to look for accurate, like 6 decimal places type of answers, DFT is not where you want to go or use for these type of problems. But if you're looking for correct qualitative trends, if you employ the right approximations, such as functionals, you can usually get reliable results if you benchmark them enough.
Aaron, may I ask?
So that's one component. Yes.
I don't know if you were planning to introduce the concept of density metrics later on for the dynamics. But if you are considering to introduce it, one of the options will be to get to it right here in your last line where you compose density out of orbitals. One could place the weighting factor between sum and pairs of orbitals and run summation over non-coinciding indices and like phi I and phi j, and then put the weighting factor density matrix. I'm not sure if it is the best place to introduce it, but it will be the minimal effort to explain what it is.
Mm-hmm.
Like weight coefficient, explaining how the density is composed of pairs of orbitals.
And so I was done with the electronic structure slide. Onto the next one, but it hasn't seemed to, there we go. So one component that we need is electronic structure. We'll cover that. Probably the most competitive aspect of our research is computing electron-phonon interaction, which as a summary essentially describes the ability of charge carriers to give off heat or to donate some of their energy to lattice vibrations in the nanomaterials we study. And the overall goal is to determine which vibronic frequencies mix together different electronic states. And there are two equivalents with different methods to do this. So on the left-hand side, we have a on-the-fly method, which is what we implement in our group. So I'll go over that first and then describe the other method next. And so the on-the-fly method essentially means computing non-adiabatic couplings along a molecular dynamics trajectory. So the starting point is to treat nuclei as point particles and then tell them to follow Newton's equations of motion, which is this leftmost equation, so which is simply just F equals ma. And then the forces come from the DFT calculations. They provide, so at each time step it creates new density, which updates the force to push the nuclei in certain directions. And I should mention that the velocity of the nuclei are constrained to a temperature, which is the second equation. So the kinetic energy, or the sum of the kinetic energy, is set equal to the temperature, essentially. And then across the molecular dynamics trajectory, we compute inner products of orbitals, which is this green box, at different time steps. So essentially you run one step of the dynamics and then compare the wave function to the previous step. So that's how we do our on-the-fly coupling. And the benefits of this method is it basically scales the same as whatever your electronic structure method is. So in this case, it scales to end of the third because we use DFT. And since we are doing dynamics, it includes automatically anharmonic motion. So it's not like an ideal spring. But the one drawback for this method is you have to run very long trajectories to reach this ergodicity, which essentially means you just have to sample enough times to generate enough useful data points along the trajectory. And so we can compare this on-the-fly method to normal mode analysis, which is on the right. So instead of doing I guess what I want. So So I guess, yeah, it essentially just solves lattice dynamics and the harmonic approximation. And so this Greek symbol that I can't remember at the moment represents bond elongation or normal modes. So this MA is equal to essentially force on the right-hand side, which looks a little dressed up, but this G term is essentially just the spring constant, which measures the strength of the spring in various directions. And so if you are able to solve this equation, you essentially get your spring constants, which give you forces, and then you get your normal modes or frequencies of vibration. And with those, you can compute non-adiabatic coupling between orbitals by through normal mode analysis. And the benefits of this method is that essentially once you solve the equations, you have all your modes. And so you can include temperature effects through a Bose-Einstein distribution, which essentially just tells you which frequency modes are activated at certain temperatures. So if you wanted to do a temperature study, you wouldn't have to recompute all your normal modes, whereas with molecular dynamics, you would have to run multiple trajectories at different temperatures. So that's one of the benefits. But I guess the cons of this method is that it's in a harmonic approximation, so it's not easy to generate anharmonic terms, which for some materials can be important for their relaxation, and it is more expensive than molecular dynamics. It scales to end of the fourth. And so you could reach a point of trade-off where your system becomes too big for normal mode analysis.
Aaron, may I ask?
Yeah.
Please think if it would be beneficial to swap normal modes and on the fly. I do not have certain answer, but if you present normal modes first, everyone is aware of this concept. Then you introduce the challenge that it doesn't address unharmonicity, and then you tell, but we do have on-the-fly method that solves this problem. And it would be more digestible for physics audience.
Okay.
But think twice. There are pros and cons in each arrangements. Just think if you would find it beneficial.
Yeah, originally I did have them swapped, but I thought with on the fly first, since that's the main method we use, that's why I presented it first. But I guess for like a story, it could make sense to change their position.
Mm-hmm.
So, next slide. And then finally, to describe light matter interactions, I haven't completely filled out this slide yet, but basically, our research group, we implement independent orbital approximations. which essentially treats charge carriers as separate and that they don't interact with each other, which has the benefits of low computational costs, so the cost is quadratic, and the cons is it neglects excitonic effects. Whereas if you use more robust theories, which computes interactions between an electron and hole, they're 2 orders of magnitude more expensive. But you are able to include more exotic effects, such as exciton binding energies. And if you wanted to describe energy transfer, which is important in some device cases, you would have to compute these excitonic states as well. But for our research, and there have been other studies that for qualitative trends, independent orbital approximation works fairly well. For oscillator strength, so the intensities of the transitions don't vary much, but you just lose the Coulomb binding energy, essentially. So as a first approximation, independent orbital works pretty well. Next slide, I'll be on.
Aaron, may I contribute a comment?
Yeah.
I look to myself, Simu, but my comment here is again, would it be beneficial to swap these 2 segments in the following logics? If you introduce beta salpeter time dependent DFT first, you immediately throw like a standard for all effects, then introduce challenges that it is good but it is too expensive, and then you offer solution as independent orbital approximation, something that we accept standards in the community, but we want to fight their shortcomings, and therefore we use approximations. On one hand. On another hand, between this left and right components, I'm not sure if there will be enough time, but you may prepare it as a backup slide or just put here one more equation and use it if anyone asks. There is a connection. So the Y sub n is transition density matrix, right?
Yeah.
So it is summation over all possible pairs of orbitals, one occupied and one unoccupied, with certain weighting coefficient, which is specific for each eigenstate number n lowercase. And then it makes immediate connection to the density matrix that you may want to introduce before and you may want to use later. But then I do not type it or write it here, but I can send you the Journal of Computational Theory, GCTC by Yulun from 2017. You may have seen it, where this independent orbital approximation is introduced literally. Like if the transition density is a summation of multiple pairs of orbitals, right? Then one can approximately tell that in this list of pairs, there is one leading pair that contributes the biggest contribution. And we keep only this leading pair and neglect all others. under this approximation of neglecting this vanishing pairs of orbitals, we are making continuous transition from beta salpeter to independent orbital approximation. So we use it as a true approximation, not as a human design, like arbitrary design, but as a limiting case of beta salpeter and TDDFT.
Mm-hmm. We basically just don't include this K.
Right? Yes.
We set K equal to 0.
We either set K into 0, you are correct, or we solve beta salpeter and then neglect all but one pair for each eigenstate. And this idea of keeping only leading term in a series is like a standard trick in calculus. So anyone who sees it is happy to accept.
Mm-hmm. That makes sense.
Should I go to the next slide?
Yeah. So the last couple of slides have been just demonstrating the methods that we use to characterize our models. And so here I'll just take a couple of slides to present the material I'm focusing on and then move on to application. So here's the material I'm studying are these so-called lead halide perovskites. And so within the last, I don't know, 10 years, they've become a very popular material in the energy field. But they've always been around in some sense. So the first published report of these lead halide perovskites was in '58, which was just looking at the crystal structure of these materials. And then in 1981, there were some physicists that just used some tight binding analysis of these materials, but I put it in here because in this paper, Dimitri's old thesis advisor was a part of the publishing authors on this paper. So it's just a reminder that a lot of these fields are cyclical. The materials kind of come and go into the research spotlight. There hasn't been and in between there, I couldn't find a lot of papers that were trying to apply these materials. But during the 2000s, there was a research group that were looking to use these for at the emission properties of these materials, trying for lasing. But then in 2009, there was, I don't know, some poor postdoc that was probably just trying different combinations of materials for solar cells to see that they work. And he was able to use some lead halide perovskite precursors in a solar cell, and specifically dye-sensitized solar cell, which got 3.5% efficiency, which for dye-sensitized is like no small feat. So it got published in a good journal. But then after that, it kind of exploded. We had different researchers trying to essentially one-up each other, trying to make the best solar cell. So in 2011, there was a group who made 11% efficiency thin film solar cell. 2015, there was about 20% solar cell from Los Alamos, and people are still competing about that. And I think at this point, they're pretty close to being commercialized or being competitive with silicon, which is around 20. But then I leave off at 2015 because there was this paper published on quantum dots or nanocrystals that were made out of these materials. And so this fellow named Maxim Maxime Kovalenko from Zurich published on these, and he's a synthetic chemist who likes to make nanomaterials and then try to find ways to implement them in technology. And so this was a nice paper that kind of brought all those together. So he made these quantum dots, and by changing chemical composition and through changing size, you can tune their emission properties through the entire UV spectrum, so from 400 to 725, which is shown in these A and B figures. And then C is just showing that they do indeed make tiny little cubes. So they are like nanocrystallines, so little cubes or experimental representations of particle in a box, which is a standard like textbook that a lot of people see in introductory courses. But then the reason these things are so useful is shown in this last figure, this piano-looking figure on the right. So I'm not exactly sure how they make the X and Y axis, but essentially what it characterizes is the color spectrum that's used for commercial displays. And these white regions represent the conventional or standard displays for televisions on the market now. So those are the color purities that they can get from materials, whereas these black dots represent the color purity of these lead halide perovskite nanocrystals. So essentially the main takeaway is that the blues are bluer, the greens are greener. Or they're a lot greener than what you can get with other technologies, and the reds are redder even. So they're very popular for light emission, and that's the model that I'll be focusing on for the next slides. So I'll spend a couple of slides just describing how we came to the model, how we constructed it, and then just some discussion on the possible surface chemistries it could have. And so just to show Andre that I was paying attention in a solid state class, I show here the smallest unit cell that is needed to create these materials. And so it has a chemical structure that's commonly referred as ABX3. So A is just a filler material used to help keep the structure stable. B is the lead of the lead halide perovskites, and this X are the halide anions. So that's the unit cell. And then to make our quantum dots, we repeated the unit cell 3 times in the X, Y, and Z direction. So that's the next slide. So if we replicate the unit cell 3 times, this is more or less what we're left with, is a lead halide perovskite cluster. But then to make these stable or to reflect their surface chemistry and experiments, we have to choose how to passivate these surfaces. Because if we just left it like this, it would run into another cluster and just want to coalesce. So essentially there are 3 strategies you can use to passivate the surface. So on this left-hand side on the top, you can have an ammonium bromide, where the bromides attach to the gray leads, and then the ammoniums take the place of cesium. We can have ammonium oleates, where these oleates, or these red ligands attached to the lead, and ammoniums replace cesium. Or we can do ammonium oleate, or cesium oleate, where the oleates bind to the lead, and the cesium take their normal position on the surface. And so for the model that I'll be presenting for the rest of this presentation, we chose to use all organic ligands, just to kind of stand out from our competitors. in this respect. And so overall, it's about 1,000 atom system and 2,800 electrons, so it's kind of pushes the limits of our computational capabilities, so it's right on the edge, so it's in the leading role in that respect. So then next slide. So we construct our model, and then using the DF density functional theory software, we optimize the geometry so that it reaches a stable minimum point. And just to give an overview of intellectual contributions to apply to this model. So there's one, I guess, technical problem where these lead ions, they have 6, for the electronic states we care about, they have these 6 p orbitals, which have a very high or large spin orbit coupling. So essentially that means that the electrons in the valence of these orbitals, they experience very large rotational motions in a sense. And so you can't use conventional EFT methods to get correct electronic structure. So our solution to this problem is to implement non-collinear DFT, which allows for the description of spin orbit coupling. So it allows eigenstates which have spin up and down contributions. And that's described by the SPI SKSO, or spinor cone-sham orbital, where it has contributions from alpha, spin up electrons, and then beta spin down electrons. And then the energies are corrected using this spin orbit coupling Hamiltonian, which is implemented into the software. And so some of this work was already worked on previously by Dr. Han in a paper, I think, for their dynamics. For that paper, but anyway. And so just to compare the difference in the electronic structure between conventional or spin-restricted DFT and then the non-collinear spin orbit coupling calculations on the left. If you don't include spin orbit coupling, you get a band gap of 3.1 eV, and then the density of states, I guess I'll mention it. Whereas if you include spin orbit coupling, the band gap shrinks to 2.4 eV, so it decreases by about 0.7 eV. And if you compare the density of states for the conduction band, is that there are major quantitative and qualitative differences. So here it's kind of decays, flattens out for the spin restricted, but for spin orbits, you have some electronic states which are spread out further, which create subgaps in the conduction band, which will be important when I talk about the non-radiative relaxation. Next slide. And so this slide I include for 2 reasons. So first is to introduce a naming convention for electronic transitions, which will be used later in the presentation, and also to show that the calculations from DFT kind of follow what you would intuitively expect for the model in terms of how their orbitals look. So first I'll mention is that for quantum dots, it's a convenient notation to describe certain energy levels by the symmetry of their orbital. And that symmetry comes from the fact that their wave functions can be thought of as two contributions. So you can have an envelope function, which describes the slow varying or the slow changing part. Then you have atomic centered functions, which describe the fast changing. And so these S, P, and D refer to envelope functions, where S refers to spherical symmetry, E refers to P, or odd symmetry, and then D is even as well. So it's similar to atomic symmetries for orbitals. And if you plot the orbitals, you can you can see pretty clearly that the envelope function for this SH orbital looks how you'd expect for a spherical symmetry. So it's peaked in the middle, and then it kind of decays the further away it gets from the center. I guess maybe another way to say it is, yeah.
Would you agree to mention that these indices SPD have some relation to angular momentum in central spherical symmetry?
Yes. So yeah, I guess, yeah, they do come from angular momentum.
Mm-hmm.
And so the takeaway from this slide is that the orbitals follow general expectations, which is important because from our electronic structure calculations, we need good energies and good orbitals. And so this is just a check to make sure that our orbitals follow expectations. And then finally, I'll describe studies of radiative and non-radiative dynamics for this model. And so here's where a video would be. So basically just shows the atoms vibrating, or the nuclear vibrating for our molecular dynamics trajectory. And then at each time step, the orbitals or the energy of the orbitals depend on the ionic motion, which is the equation in the middle of this figure. So at each time step, the orbitals fluctuate approximately harmonically due to fluctuations of the ions. And so we run our dynamics for 1 picosecond to generate enough data points. And then we compute our non-adiabatic couplings along this trajectory, which is this bottom equation. And I know that we use the spinor orbitals. And so we compute our couplings. And to make them useful for our dynamic equations, we have to turn these couplings into rates or frequencies. And to do that, we take correlation functions. So this first equation between non-adiabatic couplings in the time domain, which is this MIJKL. And then to get frequencies, we take a Fourier transform, which gives us this big R, IJKL. And this R term is what we refer to as the Redfield tensor, which is named after the person who first wrote down and solved these equations for a couple of charges and nuclei. And so this red field tensor is visualized in this right figure. So the x and y axis is orbital I and orbital j. They refer to electronic states. And then the z-axis represents the rate of transition between orbitals. And so this leftmost block describes transitions within the valence band. And this rightmost block describes transitions within the conduction band. So now we have our rates of transitions. And then to describe the dynamics, we use density matrix equations of motion, which is this ET rho term here. So it follows energy conserving transitions, which is this H comma rho term. And then there are dissipative transitions, which come from our red field tensor. So essentially what we have is we have a first order differential equation with time independent coefficients. And so essentially we just code up differential equations, and then based on initial conditions, we let the dynamics. And that leads into the next slide. In principle, you could choose any initial conditions, but since we focus on photo-induced dynamics, we choose initial conditions which correspond to a Bright's optical transition. And those are represented by the vertical dashed bars. So we have a hole state in the valence band and an electron state in the conduction band. Next slide.
Aaron, may I contribute?
Yeah.
So please decide if it would be reasonable to add a slide between initial conditions and green figure by showing occupations of individual orbitals as function of time. This is not your main result, but logically it will calm down the picky audience and will literally direct the train of thoughts. Like one slide ago we did show density matrix equation of motion, and here is the solution how these elements evolve in time. So we fulfill the original promise. And now, after it is done, we are looking for efficient way to convert these trajectories of density matrix elements into observables or into some visually appealing form.
That makes sense. So from changes in populations, we can compute expectation values along the trajectory. And so what this green figure shows is changes in expectation or energy expectation value for the electron, which is the orange lines, or I guess, no, that's the dotted line. Whereas the orange represents charge density of the electron. And then for the hole, it's the solid black line, and then the blue represents the decrease of hole density. And so essentially, for the electron hole, we have energy decay. And then to get the cooling rate of the charge carriers, we fit the rates, or we fit the decays to a single exponential, which is this KE. And then for both the electron and the hole, their overall cooling dynamics are roughly the same order of magnitude. So it's 100 for the decay to their lowest energy states, and 1 to 200 femtoseconds. So if you look closer at the electron decay, it does show a little bit more vibrant relaxation dynamics than the hole. And then to drive home the point of how important spin-orbit coupling is for to accurately describe the dynamics in these materials, I compared the decay with spin-orbit coupling compared to if we did not include spin-orbit coupling, or just used spin-restricted DFT. So on the left, so in this left figure, we see that there seems to be two decay modes. There's a faster decay, and then it slows down as it gets closer to the band edge, or gets closer to its lowest energy state. And this is attributed to large subgaps, which form in the density of states. So directly right to the figure are these blue arrows, and those represent the spacings between electronic states. So you see for the lowest energy transition, there's about 0.2 eV subgap, which compared to thermal energy is very large. And so based on this consideration, you would expect that there would be a slowdown of the relaxation once you get closer to this state. But if you compare it to without including spin-orbit coupling on the right, is that the decay follows very fast single exponential, and it decays, I don't have an exact number at the moment, but it looks like sub-100 femtoseconds, so almost an order of magnitude quicker than when including spin-orbit coupling. If you look at the density of states, it's this makes sense as well, because without spin-orbit coupling, we don't have those very large subgaps, which helps slow down the cooling. So that describes the non-radiative relaxation. But along the same trajectory, we can compute radiative relaxation, or the probability that the model will emit light instead of heat. And to compute those, we compute transition dipoles and average them along the trajectory, and then essentially use Einstein coefficients to get rates of transitions, which is this AIJ term. And so during the dynamics, that's what this blue figure represents. So early in the dynamics, there are these low intensity IR transitions, which is this yellow bar around 0. And those just come from the carrier cooling. But once both the charges relax to the band gap energy, it emits very intense photoluminescence, which is shown in this very rightmost figure. The spectra being dominated by the photoluminescence signal. But then to characterize, so this shows that its lowest energy transition is bright, but to get an idea of how efficient the transition is, we compute a theoretical photoluminescence quantum yield, which is this bottom equation, which essentially is just the rate of the radiative relaxation over the sum of the radiative and non-radiative. And due to the radiative and non-radiative essentially being on the same order of magnitude, we get an efficiency of 53% computed, which is fairly agreeable with experiment. And so, summarizing all this, the main takeaways is that without spin orbit coupling, the hot electron cooling is too fast, and that when we include it, we see an interesting slowdown near the band edge. And then from describing how efficient it is, we get results that compare favorably to experiment in terms of the radiative relaxation and the quantum yield. So that brings us to the last section, which is the proposed proposed research part of the comprehensive exam to work on before graduating. And so there are two components which essentially work together. But first I'll describe the methodological development and then the model system that we plan to implement the models on. And so over the next couple of slides, I'll just make a statement of the problem and then our development beyond the approximations that are used. And so an unstated approximation for all the previous dynamics results is that the forces that act on the nuclei during the molecular dynamics trajectory are approximately the same as the ground state forces. And so the changes in the nuclear motion are essentially the same between ground state and excited state potential energy. And that's what's illustrated in the figure below, where the curvature of these parabolas are essentially exactly the same. And at the valid approximation, you're considering stiff, rigid, covalently bonded materials such like silicon, or if you look at their Young's modulus, it's at something like around 100 gigapascals, which indicates that it's very resilient to strains when it's stressed. The next slide. But if you consider softer materials, which perovskites generally fall into, this approximation may not be the most valid. And so it may not be the best approximation to use the ground state dynamics to compute couplings. And so this table on the right, this just shows that the Young modulus value for these perovskites are at least an order of magnitude lower. So they're a lot more soft and squishy. So if you photo-excited these into the excited state, the curvature of their potential energy surfaces are likely to change. And so a direct result would be that their non-adiabatic couplings would be different as well. So then to overcome this assumption, the goal is to incorporate explicit excited states couplings into the red field dynamics that we implement in our group. And so essentially, it comes down to computing non-adiabatic couplings for various electronic configurations, which I label with this X superscript. So it's transitions between orbitals I and J, but under different electronic configurations. And then the main challenge is how to convert these couplings into propagating the density matrix, or how the changes in populations should occur. Yes.
I know what your plans are and where this equation originates from, but formally there is missing equation for rho sub x. Like mathematically, if we want to solve this set of equations, then it's not clear where rho sub x is coming from. And it seems very natural to connect it with your previous explanation of radiative and non-radiative recombination when at the point when you were computing the photoluminescence quantum yield. Like rho sub x of t will be exponential minus in the power minus recombination rate times t, right? Or one can put just differential equations ddt of rho sub x equals minus recombination rate times rho sub x.
Essentially, yeah.
I'm not complaining, but if your audience will be populated with mathematicians, they don't care what. Well, I shouldn't say it so, but the primary question is not implementation and interpretation of the equations, but possibility to solve them, so that each unit is defined or self-consistently dependent on something. Like okay.
Yeah, I guess I didn't have exponential decay in mind. That's essentially what it would end up like. That's what the solution would be.
Right, and then
changes in each subcopy. Yeah. And then an example in a couple of slides.
Yep. And then for practical implementation, it is basically nothing. It's one line of code, and then you can add this line of code in any calculations you did before and double number of papers. Should I swipe to the next slide?
Yeah. So that's the methodological development, and then the model that we plan to apply this to is a relevant Perovskite system, which includes specific occupations of excited states, essentially. So this is a slide on previous work that Dimitri and I have already done. So we considered whether if you just add a single charge to the model, so that's this leftmost figure. So if you add an electron, and in perovskites, the common nomenclature is to call these polarons because these charges deform the lattice since they're soft. So in this case, we had a negative polaron and essentially ran the same bells and whistles that was presented for the non-radiative and radiative dynamics. So we did the same thing where we removed an electron or introduced a hole, which is the positive polaron system in the middle. And from this study, we did find that if you include explicit occupations in these bands, that they do have a noticeable impact on the non-radiative dynamics. So this arrow comparing blue and green lines, that shows that if you explicitly account for charge in the conduction band, it slows down the radiative dynamics. And then same for the hole, comparing the black and red lines. So it's a system we've already worked on. And then our model is to essentially combine both these models, so to reflect the photo excitation of a physical system. So if you photo excite and then let the charges cool, you would have an electron occupying this SE band and a hole in this SH. And those are visualized in this middle and right figure. And it shows that you would have a different potential acting on the nuclei because there's like the charge isn't uniformly distributed. So you have positive charge located in some regions and negative in others. And so that will influence the dynamics of the couplings. Next slide. And so the previous figure was just an example of one configuration. But what we want to do is model the PE to SC or pH to SH relaxations. So we compute various electronic configurations reflecting these occupations, and we screen for singlet configurations and then triplet configurations. So we just do our homework and look at different spin possibilities that can happen during the dynamics. And then for each of these configurations, we run a molecular dynamics trajectory and compute a set of observables. But mainly what we want is non-native coupling. Next slide. And so I haven't filled this in yet, but this is just an example of how the dynamics would evolve. So say your initial condition is you have a charge occupying the PE band at time equals 0. And so the change in occupations of that band at time 0 will be weighted fully from couplings computed in that configuration. But as time goes on, you'll have population change from the P state to the S state. And so you have a gain in population in the P and the SE. And so as time goes on, you'd have a weighted contribution of rates from the both electronic states. Yes?
Same question as to a few slides ago. Rho S sub E should be either defined or an equation for it should be explicitly included, or just d dt of rho sub S sub E equals, and then similar, just declare that it will be similar. The equation that you are writing looks like it is inspired by approach by what Andrei and his team are doing, and this will be set of nonlinear equations that cannot be computed by diagonalizing of the operator matrix. So it should be literally propagated step by step, and it may lead to bifurcations or instabilities, which is fine. This is favorite toy of mathematicians, but there is a lowest order approximation to these nonlinear equations when you will linearize it, like assuming solving this equation under assumption that rho sub PE doesn't change, and then solve only for rho sub SE. and like set sort of perturbation theory, and we can talk in person more about it, but it is quite a standard thing related to what we discussed a couple of slides before, and one can include it right away here in the slides. Like lowest limit when this nonlinear equation can be solved, approximately solved, without solving nonlinear equations.
Mm-hmm. So that's essentially expanding the bracket terms.
I'm going to write something. Neglect explicit time dependence in one of the nonlinear term. Like find a trivial solution as a reference point. Because solving any nonlinear equation without tricks, without approximations, is always a risk. Should we go to the next slide?
Okay. Yeah. I think that might be the last.
Uh-huh.
And yeah, this is just the typical workflow for a project like this. So there's 3 different components. So the DFT-based components of doing the modeling, and extracting observables from the DFT calculations, and then doing our home sweeps coding of the Excited-State Dynamies. And then each of them can be broken into different phases based on, I guess, just bottlenecks and how these calculations are generally done.
Mm-hmm. What could surprise or like make it not smooth in perception of the audience. Typically, observables are considered not as intermediate step, but as a terminal, final step. Like maybe after radiative and non-radiative dynamics, you have last terminal step of ultimate observables. And here where you tell extracting observables, it's like lower rank observables. It's just doesn't fit into standard teaching or learning of quantum mechanics when one is doing some calculations, then getting observables, and then instead of comparing them with experiment, they just used to run another calculations. I completely understand what you're doing. It's just a way of visualizing and verbalizing it in more standard way, so that make it easier digestible.
Mm-hmm. You know, I think when I made this, I was thinking in like time for each phase.
Mm-hmm.
But, mm-hmm.
No, I'm at your side completely understanding what is going on. It is not the search of ultimate truth, but a way to present it to someone who is outside of the group and match expectations, so that it doesn't contradict like expected flow of steps.
Okay.
Is it the last slide?
I think so. You can check. The last one is acknowledgements.
Sure, I cannot wait listening to this. Okay. Let's thank Aaron for a lot of intellectual effort to organize this materials, and let's try to ask some questions. Fatima?
I have a question.
Oh, okay, Yulun, yes, please.
So I guess I'm very confused about your proposal section. So your last slide just showed your plan for to address this problem, right? But I guess in the beginning you already showed some results, right? So I guess maybe you can just modify the order of slides.
Which one do you mean that I provided results for?
Maybe 3 slides back, I guess. Yeah, and also maybe 1 slide back. Yeah, right here. Is this your preliminary results?
So the reason I put this slide in is to introduce the idea of polarons firsthand. Second, to show we've been working on this, are working towards this direction already, so that I'm just not hopping into this model. And yeah, I guess I just put this figure in to show that like the rates of transition do change if you consider like which electronic state the models are in. So it's more motivation to look at more couplings to see if the rates change, if they remain stable and there's not a lot of change, or if they even change more dramatically.
Okay, so I guess for your proposal, your major focus is just the simultaneous polaron, right? But here you just show individual polaron, so that's a difference.
So you would have so if you compare these figures, like these bluish figures, to the one on the next slide, like for the individual polarons, it's either negative charge throughout the crystal or just positive charge throughout the crystal. But in the case of if you have both electron and hole, you can see that there's different charges localized, well not localized, but they're distributed unevenly in the crystal.
Okay.
So in that respect, there's motivation to think that the forces on the nuclei will be different. On one hand, but on the other hand, it's like you have positive and negative mixed up in a box. Like they could just cancel each other out. So the results could just be similar to if we just ran a ground state calculation.
Can I make a comment? So in one of the works that Yvonne was preparing some times ago, there is a image for browsing in a space of approximations. Yvonne may share it with you if he wants, but I can just communicate the idea in application to your proposed research. And it's not final form. You may modify and wrap it up. Like assume a cube in a space which not a Cartesian space, but space of ideas, space of approximations, and each of the three directions is maybe excitons, polarons, and dissipation. And ground state DFT is origin, where nothing of those three is implemented. Dissipation is when we standard just go one in the like x direction, when we go do only phonon-induced relaxation, and then if you go both onto relaxation and polarons, it will be something that you are about to do, and ideally one may want to do all three together, like to jump from origin to the opposite side of a cube. And I interpret the original question of Yvonne to your flowchart workflow diagram that it mostly summarizes what has been done rather than includes boxes for the future steps. It is quite challenging. It's hard to sell what hasn't been complete yet, but one can make maybe a little box outside of this main area, make it like a cloud fluffy style and type like unknown future step. I'm not sure if it is the right thing to do, just throwing in some
I guess the only other example I've seen, they provided a few figures. So one was like a workflow chart, like the one I have. And then they also had like a timetable chart.
Yes. Oh, then then what? I see. It's a great idea. It's a great idea. Yeah. Then maybe one can introduce phase 4, right? And it will have only one box in the middle under extraction observables, and then one would connect radiative, non-radiative dynamics down and to the left to the phase 4, like observables for coexisting polarons. Yulun, would it satisfy your criticism?
Yes.
Okay.
Oh, I see what you guys are saying now.
Huh?
I get what you guys are saying now.
Okay.
That usually, yeah, okay, there are steps after computing dynamics. There's another interpretation step.
Mm-hmm.
Okay.
Fatima, do you have any suggestions or criticism?
I don't have any questions, but I think the talk is longer. It needs to be shorter.
Well, yep. But maybe Aaron was pronouncing, verbalizing, practicing this talk for the first time, and it was a process of online active thinking. If Aaron just makes some changes and then practices, recites it once or twice again, just for himself, it will take like twice as shorter time.
Mm-hmm.
So
I think without transitions, there's like 30, maybe 35 slides of actual content. And a lot of them should just be 1 minute. And then for the heavier duty, for the slides with a lot of information, it's just getting those down to like 2 minutes a piece. If I had to get rid of anything, remove some of the introduction, just because I put that in as filler. Anyway, so.
Did you have another question or suggestion?
Yes, so can you go back to the slides where you show the potential energy surface when you first introduced polaron? So, yes, right here. So I guess right here, you said that the potential energy surface is different for soft materials. And in the table, this is about hybrid inorganic organic perovskite, right? But actually, in raw calculations, you just focus on inorganic perovskite. So why you make this kind of transition, and how different for hybrid perovskite and inorganic perovskite in terms of polaron?
Bottom lines are for organic, right?
Right. This is just the only table I could find, or it was the only good table I could find for perovskite. But cesium is basically the same. Because the deformation is just like the lead halide parts. Yeah, I should mention that before. I should mention that while I'm talking. That cesium is basically the same.
Okay.
Okay. I was trying to make a recording, so if it was successful, I'll share it, just in case, Aaron, you need to take some of the, if you are not taking literal notes, it should be available. But thank Aaron once again. It's really a strong intellectual effort, and if you polish a little bit, I think it will serve its purposes. So I want to check if all of you or some of you will be available 2 hours before Aaron's presentation on Thursday to join the class as reviewers. Okay, thank you, Ilan. Thank you for confirming. Fatima, does your schedule allows it, or you are busy? Probably your microphone is muted. You can just show yes or no. Yes or no? Yes or no?
No, I did not understand.
Okay, so in 2 days, well, literally less than in 2 days, maybe in 40 hours, Thursday morning, 11 a.m., there will be students in computational chemistry class will bring their written reports, and we need to play a process of editors and journals. So I need help, and if your schedule allows, your help is appreciated. If you cannot, just let me know. I will try to recruit more editors. Since everything is done online, it means just connect and do some forwarding of the papers between students.
This Thursday?
Yes, this Thursday.
This Thursday, I don't think, but I will try.
Okay, then, okay, let me know as soon as it is clear. Aaron, you have all rights to decline, but just in case, I want to ask you, how would you feel 2 hours before your committee presentation?
I can try. I guess it's at 2 instead of 1.
Okay, then you'll have the whole 2 hours to relax. Okay, yeah, many thanks. I believe it will be easier than in person, but let me share plans how we will organize. It will be same idea, same forms, but everything will be online. So students will, like I will announce them emails of editors and ask them to send the requests, like submission of the manuscript. Probably it will be either attached document, or I will try to ask them immediately to prepare Google Docs editable document. And then I will also provide the map who are the best reviewers, and you just take link to the Google Docs document, forward it to the reviewer, and after it is done, after reviewers type in some comments, you send back the link to the author. Okay, yeah. Many thanks. I didn't invite students to request help from group members because now everyone is busy. But maybe after reading their write-ups, you may decide that some of the students can be of help for you, or may need help, and can be used as the potential seeds for common research effort. So you may like some. I know that Salim, he is not. He didn't have time to invest all of his intellectual strengths, but he is from Eric's group and he is interested in the similar objects as Aaron is interested. So he can learn a lot from you and others as well. Okay. Are there any other subjects to discuss? Okay, yeah. Many thanks. I will send a separate email to Yulun with update about catalytic project with more information, just to save for future use. Okay, then I do not have any other items in the program, and I suggest we disconnect unless there are more questions. Okay, then have a good evening. Oh, yeah, I need to send it.
I know all the deadlines have been passed already. So.
Do not worry. Do not worry. It will be submitted.
And how about, I'm not worried, but it's not time, that's why I'm asking. And how about this graphene?
I'm waiting for Venji. As soon as he sends the materials, I'm inclined to send it out immediately.
Oh, he sent me feedback.
Okay. Yeah, please implement if to the best and forward to me. And I was going to submit it right away after seeing version, and then I decided just to give him an opportunity to contribute something. And
okay, well, I'll implement them then.
Huh?
I'll send it to you. I'll implement his suggestions and I'll send it to you.
Okay, yeah. Very good.
Okay, let's.
Yvonne, do you have any aspects that we may need to discuss?
Yes, so you just said you'll send me some materials about the catalyst, right?
Yes.
You mean the nickel?
Yes.
For the job, right? Okay. Is this some computation from line?
Mm-hmm.
Okay. So, because right now I'm trying a new set of data for transition state search by including spin. So I guess right now my calculation is converged, which is good news. The activation barrier is like 0.4 nanovolts. But I'm not sure how reliable.
How many electron volts?
0.4.
Okay, I think it is reasonable. Their reaction is happening in room temperature, which is much less. But if the width of a barrier is small, and if we implement the quantized nuclear effects, then it should be like in your rocket fuel project. The barrier was higher than 0.4 eV.
Okay, so I guess the major information they want from us is just a transition state, right?
Yes, and there were some details that you may, they're not centers, they're side comments, but you may just get acquainted with them and adjust the direction of your search.
Okay.
And I don't know what are the plans of Beijing, but and what is his style, but I think with the results that you already have, one can plan on preparing manuscript or enough materials for a manuscript. Since he is paying, in this project he is the boss, but I would be interested in maybe give him an opportunity for like using materials and immediate submission, or blending it with experimental data. And in this aspect, if you merge the